Okay, everybody. So now it's time to continue on with differential equations, video two, and so this is something that you're just going to do is being able to translate from a verbal description to an equation for a differential equation. That's just something that's one of the skills involved. So this one, so x of t looks like the position, and the acceleration is inversely proportional to the square of the time. What would that be? In the 45 seconds, they're just saying during this period of time, this formula works. So that's just kind of the domain. And so acceleration, I'm just going to say x double prime of t, right? Because if x is the position, velocity acceleration is equal to, and what is the equation that can model this? What is it? It's the acceleration is inversely proportional to the square of the time, is k over t squared. Sweet. So all we're doing is just representing verbal stuff with an equation. The volume is given by a differentiable function v, where v of t is measured in liters. Okay, so we got t, we got v of t. The volume increases rate with respect to time, so dv dt at a rate that is directly proportional to the product of the time and the volume. So that's directly proportional to the time and the volume. All right, so that's directly proportional to the time and the volume. And one thing is that in this situation, they gave us enough information, we can actually figure out what the k is, I think. So they told us what the volume is, and they told us how fast it's increasing and when, so we actually can figure out what this k is. So in this case, so the dv dt, it's increasing, that's positive, at a rate of 2 liters per hour, and it's directly proportional. Yeah, okay, I'm just double checking my work. So 2 equals, and k we don't know, and the time is at t equals 5 hours, and everything is measured in hours. Great. And the volume is 100. Whoa, that's a weird constant. So 500 divided over, so k is equal to 1 over 250? Crazy. And so then dv dt equals 1 over 250 times tv. Okay, and that's all we're doing is just representing them at that point. We haven't learned how to solve these things yet. That's coming later. And that is actually a differential equation that we will be able to solve later on. Okay, so another thing that we mentioned earlier, but just kind of giving you a couple of examples of it, is verifying solutions. Which of the following are solutions to this? And so you're going to have to just kind of go through each one of them and see if they're solutions. So I'll give you a chance to do that in just a second. And then, and this one, when would this be a solution to this? So I'm guessing we're going to have to verify the solution, and somehow we're going to figure out what k is. Interesting. And finally, it has this, y prime equals this, and y of 1 equals 2e, which is the following. Okay, these are just 3 problems for you to do. It doesn't involve any more information than we've had before. And so I'm going to pause the video and just write up the answers to save you time on the video. So try these ones out and see if you can answer them, and we'll see if we get the same answers. Okay, I'm pausing. Okay, I did my answers really fast to try to get the video done, and so I apologize if there are any mistakes in here, but and you don't get a chance to correct me in class. Oh, the best part of school, but that's okay. So so the first one didn't work because the signs are wrong. They're both negative, so they won't make 0. But the second one works because each time when you're taking the derivative of e to the 3x, then it's cranking out a 3 each time by the chain rule, and so it works. And then the third one is just confirming that it didn't really matter what was in front. Like 2/3 was fine, but it could have been something else, and it would also have worked. Okay, cool thing. Second one, I just took the derivative, and again, an e to the 3x. That was kind of funny. I got these problems from AP Classroom because I never had something quite like this in my notes, and I thought, okay, I'll throw it in. And so again, they have an e to the 3x. I don't know why they're such a fan of that. And remember, you don't have to use product rule. I often see that mistake with this because k is a constant, not a function of x. And so therefore, you can just bring it along for the ride. And so when I did the derivative, I got this thing, and then I just copied and pasted it down here. But I could cancel out the 3e to the 3x, that's 9, and then 9. And so I'd get negative 3k e to the x. And so I could add 3k k e to the x to both sides, and that would give me 2k e to the x's equals e to the x. So 2k has to be 1, so k is 1/2. And this one, I just from problem solving standpoint, I want to mention how I did it. I first looked at, okay, which one of these, if the x is 1, is the y2e. And so I could cross off the first one because that would be e squared plus e, and this one, which would be 2 plus e, not 2e. So I crossed off a and c right away. And then I said, okay, so which one is the derivative 2e to the x plus y? And I just thought, I mean, I have to admit, I did this kind of fast, and I kind of cheated a little bit on it for speed. And what I did was I just looked at this and said, well, wait, the derivative of this is not going to be 2 to the x plus y. It's just going to be 2e to the x. So I just crossed it off based on process elimination, and I just circled that without checking it. But I'm trying to get this done fast. Okay, maybe we can get it done in 2 videos. All right, so the final thing in differential equations is a thing called slope fields. You ran into this last chapter on a problem I assigned that I shouldn't have, and so now we're doing it. So what it is a slope field is you take a differential equation that you don't know how to solve and you don't know what the solutions are, and you're trying to get a sense of what the curves would look like if they went through any given point. So for example, on this one, y prime is x plus y. So like at 0, 0, y prime would be 0. So if it goes through 0, 0, then, and let me change the color a little bit. Let me make it a little bigger so it's a little easier to see. I'm just going to make the color red just so it's easier to see. So if it goes through 0, 0, then it's going to be flat. And then I'm just going to go in some direction here. So going to this one, if it goes through this point, 1, 0, then the derivative will be 1. So I'm going to, right through there, I'm going to make a little thing with a slope of about 1, close enough. And then I'll make this with a slope of 2. So I'm aiming for, escape. So I'm aiming for that point, I was aiming for that point right there, with a slope, right there, because that would be a slope of 2. But it's not going to actually go up there, because as the curve moves up, then the derivative would change, and so this thing would curve away from that point. And it's just going to keep getting steeper and steeper, right? Now, one thing I can notice pretty fast is, if x's and y's are opposites, then it's going to be 0. So I can go, oh, yeah, it's going to be like this, and then like this, and then everywhere x and y are 1 apart, with the first one being bigger. I don't know how to describe it, but if they're 1 apart, then they're going to have a slope of 1. I think it's going to be like this one is going to work, and then like this one is 2, -1, so that's going to have a slope of 1. Like all these points, if I plug them in, they'd all give you a slope of 1 along that line. And I go, oh, and there's usually a moment when you're doing a slope field where you're plugging in numbers and you're getting values and you're getting the slopes. You could even make a table of values if you wanted to and just go x, y, I don't know why it's racing, and y prime. So when x is 0 and y is 0, y prime is 0. When x is 2 and y is -1, then it's 1. And you can make a table of values and just plug in numbers. But at some point, you often get a little moment where you're like, oh, now I know what this thing looks like, and you find ways to shortcut your work. So along this one, they've got a slope of 2, and then on this one, they've got a slope of 3. Generally, you don't have to make this many points. This is probably more points than I've ever made for a slope field in my life. But I could see the idea. It's like I could see, okay, if I go through this one, then I'm going to keep going, but I'm going to curve up because I can see this. And so I can kind of see the way the curve's going. The curve going something like this and getting steeper and steeper as you go. Now, you're not, when you make a little drawing like that, what I just did, like sort of sketching a curve, you're just doing it approximately and trying to follow the contours that it's showing you. You're not expected to have it be perfect, because that's not the purpose. The purpose is to get an idea of what the curves look like. At -1, 0, they'd have a slope of -1, so it'd be like this, Yep. And that's a slope field. And then it'd be -2 again, And I'm going to stop here. On the AP, every once in a while, they have you actually plot a slope field. And usually they only have you do 9 points, like 3 this way, 3 that way, 3 that way. Yeah, three sets of 3, because it's kind of silly. Okay, So this graph is a demonstration of the variety of curves that are all solutions to the differential equation. Sketch two of these curves. So you can just kind of pick a spot and say, all right, so like suppose, well, this is kind of interesting. Like if you were on this point right here, suppose it went through this point. And so like these are all the solutions, like the general solutions of this. But if I go through that particular point, then I can kind of see, oh, wow, if I go through this, I'm going to have a slope of -1, and then I'm just going to keep having a slope of -1. So one curve, it's kind of interesting. One curve that this could be is if you started right here, you'd actually just have this line right here. So one solution for this apparently is y equals -x minus 1. And I just want to kind of, right, because I'm just looking at it, and I'm just looking and saying, yeah, you know, it's just going to keep following those slopes, and so it's going to stay on there. And I'm just going to check this. Now, normally, I wasn't even planning on doing this. I was just, showing you how to sketch it. But I'm showing you how you can kind of see a solution and go, oh, now I know what that solution is. And so, so y prime is -1, right? And so this says y prime is x plus y. So -1 equals x plus y. And you say, wait, is that true? Well, yeah, remember y is equal to this. So I can plug in -x minus 1, and you can see that that works. So turned out, sketching the slope field here, I could actually see what the solution, one solution was. But you can see other solutions are going to be different. Like if I'm going through, say, this point right here, then I'm going to curve, and I'm going to be curving up, 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 steeper and steeper and steeper. And the farther I get out, the steeper I go. And then it can't actually be -1. It can't cross this thing, because by the time it gets close to it, it's going to turn. So it's going to be kind of like this. Like with an asymptote. I didn't draw the asymptote very well there. And I bet you down on this side, it's going to like curve down. So that's what a slope field does. It kind of gives you a visual image of what all the different what all the different particular solutions are. All right. So we were going to do this in class, and so you can try one or two of these out. Work with your partners to create a slope field for the differential equation, and then sketch two solutions. And we'll show you that in just a second. So I'm going to pause it. You can try them out and pause it. I'm going to pause it, and we'll see what your stuff looks like. And I've decided it'd be better for me to actually show you how I sketch a slope field, just so you see how you kind of save yourself some time. So one thing I notice on this is if the x is 0, then the y prime is 0. So everywhere the x is 0, I'll make the y equal to 0. And except, ooh, wait, it's 0, 0, it's undefined. And everywhere else the y is 0, it's undefined. So all these slopes are undefined. So what's an undefined slope? An undefined slope looks like this, doesn't it? Except at 0, 0, it's funky. I'll show you why in a second. And then this would be like this. Sorry, kind of overlap my graphs here. And then if you check out, like, whenever x is at 1, 1, 2, 2, 3, 3, and stuff like that, then you can see that it's just going to be -1 for the slopes. And if you plug in these points here, you can see that it's +1 for these slopes. And then it does the same thing over here. Are you getting the idea of what the solution to this thing is? Yeah, it's just circles. I mean, oh, it would have a radius of 2, yeah. So this is the differential equation for a circle. And if you try, if you take the derivative, like use it implicitly, x squared plus y squared equals r squared, and take the derivative implicitly, you'll get this. And on the second one, y prime equals 2x. Okay, so when the x is 0, then y prime is 0. So that happens again. So boom, boom, boom. And then what I notice is, I want to point this out, is that for any given x value, the y prime always stays the same, and it doesn't matter what the y is. So like if the x is 1, the slope is 2. So everywhere the x is 1, the slope is 2. So it would be like the exact same slope the entire time. And then it would be -2 at these ones. Again, you just have to get the general idea, and I'll let you know that these are parabolas, right? Because y prime equals 2x, we saw that one earlier. That's the general solution is y equals x squared plus c. Right? So, and I talked about the general solution, the particular solution. I have to admit, I rewrote the notes earlier, but this was kind of where I put it in the old notes, so it's kind of still there. And you could see the whole idea of like sketching a particular solution. But remember that at this point, we don't officially know how to solve them, so you don't have to worry about that. Okay, I'm going to finish in time. So differential equations, meaning, verify, and slope fields. Good luck on the homework. I'm done.